Next lesson. Optimization. Okay, at the beginning of the extreme values lesson, I said that people in a lot of fields often want to find out what value of an input gives the maximum or minimum or the greatest or smallest possible output, and possibly also find out the value of that optimal output level. And that kind of thing is called optimization. And I mentioned a couple of examples, or I mentioned a few examples. I mentioned trying to maximize, let's say, crop or bacterial growth, trying to pick the dose that's most helpful to a patient, trying to minimize travel time, like if you're in a car, or light minimizes the travel time, which is called Fermat's principle. You might want to minimize manufacturing costs or maximize profit. And if anyone's in microeconomics, you might talk about how you maximize profit where marginal cost is equal to marginal revenue, or average cost is minimized where average cost is equal to marginal cost, something like that. All those things are essentially calculus ideas. Okay, so you can rewrite all those kinds of things in the terms that we talked about here. And also I mentioned optimal foraging theory, which is how animals behave in terms of eating, depending on how available prey is, how often they encounter it, how hard it is to handle, and how much energy they get from it, that kind of thing. And often we find that organisms behave in a way that seems optimal, or near optimal. And I've stuck a couple of examples on the end of this, and I might mention something else in tutorial, about how that kind of thing goes on. Okay, how organisms seem to behave in a way that's good, okay, or near optimal in some cases. Okay. All right, so given a problem where we're trying to find the largest possible or smallest possible value of something, we need to model the quantity to be optimized as a function of a single input, okay? So we need to construct a model, which will not always be done for us. Something that looks like this, predictably, okay? This is the output quantity or whatever, quantity to be optimized. Okay, it's the thing that you want to get as big as possible or as small as possible. It's the output. And this is the tunable input. Tunable input. Okay, the sort of control knob you can move around to try to get the biggest possible Y or the smallest possible Y. Okay, and also associated with your model will be some sort of domain. Okay, possible values of the input, okay? That's the only places where your knob can turn. Okay, and then you want to find the global extrema. Okay, find the global max or the min. Depending on the problem, you want to find either the max or the min, or conceivably both. And you want to find the global one, okay? No one really cares very often about, where the output is a bit bigger than the surroundings. You want to find the biggest possible output. Okay, so you want to find global extrema. Okay? Okay. All right, so we're going to be using the tools of the last two lessons to do this, and you'll see a twist quite soon. And just note this is the tip of the iceberg with optimization, okay? The people who do this for a living, and they're not just taking second derivatives and first derivatives and setting stuff equal to zero. It's a lot bigger than that, okay? So this can go places. Okay, good? All right. Okay, we've got an example. Right? Good, here we go. I won't sing. Using as little material as possible, we want to construct a cylindrical can, a right circular cylindrical can, that will hold 500 milliliters. The height of the can and the diameter of its base must each be at least 6 centimeters. Determine the radius and height of such a can. I added that second bit in just now, okay, for a reason. So that won't be in the slides yet. Okay. This is a perfectly believable example, all right? You want to make a container that holds something, a particular volume of liquid or whatever. And what else? And you want to use as little material as possible to save money or to reduce waste. And you also have constraints on the dimensions of the can, okay? Because maybe a really narrow can wouldn't be easy to handle, or you wouldn't be able to make an opening easily, or whatever. So you have constraints on the design of the can. And that, oh God. This is the new adapter right here. Okay. Okay, there we go. So it's a believable example. This is the kind of thing that might actually happen, you might actually care about. You're ignoring wasted bits of material when you're cutting out the circles for this thing. You're ignoring assembly costs. You're ignoring the cost of making openings. You're ignoring the fact that you might be using different kinds of materials on different parts of this can. Okay, so you're ignoring a bunch of things, but those could be modeled as well. You could incorporate those into this thing. But we start simple. Okay, example, can. A diagram is often useful with this kind of thing. Let's draw a diagram. Okay. Top is circular, okay, not oval. I've drawn it this way because I'm an artist, obviously. Okay, there's your radius. There's your height. Okay. If this was high school, you'd go let H denote whatever, let R denote whatever. And possibly here as well, unless you're short on time. So the radius of the base is R, the height of the can is H, and both will measure in centimeters. Okay. What's the volume of such a thing? The volume is the area of the base times the height. The area of the base, it's a circle, pi r squared times the height. Okay? What's the surface area of this thing? It's the area of the top, the area of the bottom, and the area of this thing if I unwrap it, the sides. Okay? So the surface area is going to be 2 pi r squared plus 2 pi r h. Okay? Why? I've got two circles with radius r. The top and bottom of this thing, okay, that's this. And I've got one rectangular piece after I unwrap this thing, okay, whose length is the circumference of the top, 2 pi r, and whose height is h. Okay? All right, that's the surface area of this thing. All right. We are told that our volume is 500 mils. Those units will be consistent, okay, because centimeters cubed is milliliters. So that's fine, we don't have to convert anything. Okay, so what do we get? We get 500 equals pi r squared h. And I'll just rewrite that s thing, maybe. Okay, this is the guy we want to minimize. Okay? But there's two variables in here, there's R and there's H. We don't know how to do that, okay? We know how to minimize or optimize something where you've only got one input, okay? One input, one output. So what do? Same thing we did with that related rates example in the tutorial if you remember, or if you just figure it out from here. You can eliminate one of the variables and get this guy in terms of just R or just H, okay? So we'll use this guy, use equation 1, to give us this. Yeah, and then we substitute that into 2. Pi r squared plus, pi's cancel, r cancels that thing, plus 1,000 over r. Wonderful. Okay, so now we got a thing in terms of one input, and we can actually talk about minimizing or maximizing it. Tell me if anything doesn't make sense. Okay. Okay, so there's one more bit of the model that we haven't done yet, and that's the domain. Okay? What did we say? We said the height and the diameter must be at least 6 centimeters, possibly to make this thing handleable. It might also be that the store would have told you to make it at most a certain amount so it would fit in the shelves or something like that. So we have additional constraints, and they tell us our domain. Okay? Diameter must be at least 6. Okay, what does that tell you? Diameter at least 6 means radius at least 3. Okay, the height must be at least 6. Okay. What does that tell us? Well, we have an expression for the height. It's this thing. Here we go. Okay. Now, how do I want to say this? Okay, together, these guys will tell us that the radius has to be between 3 and, let's see here, the square root of 500 over 6 pi. Which is around 5.15. Okay? Hopefully that makes sense. Okay, good. All good? Okay, so we've been given constraints, and that tells us where the radius must be, okay? And there's no further constraints, okay? There's nothing else that's a problem here. That's physically reasonable, and it makes sense in here, okay? So it doesn't lie outside the implicit domain of this thing, the implied domain of this thing. This guy's happy with those kinds of values. Everything's good. That's our domain. Okay. All right, what are we looking for? We're looking for the global minimum of that thing, okay? On that domain. So what do we need to do? See if is the interval closed? The interval or the domain, is it closed? Yes, it's closed. We include the endpoints. Yes, and we have an interval, so that's good news. Okay? Trying to optimize on a closed interval. Is our function continuous there? Is this guy continuous on that domain? Yes. Okay? So we can use the closed interval method. Which says what? Which says find the critical points, evaluate the critical points, find the endpoints, evaluate the endpoints, and pick the big and the small. Okay. Okay, let's find the critical points. To do that, we need the derivative. Derivative of this guy, 4 pi r. Pi r minus, is that 1,000 r? Okay, good. Okay. And all I really used was power rules there. Okay? All right. Okay, so we're looking for critical points, or critical numbers. Where is this guy undefined? Okay, where does this guy's derivative not exist? Nowhere in that domain. Okay, the only place where you could have a problem is at 0, but 0 is not in the domain, so everything's cool. Okay, nowhere in the domain. Okay, I'm going to be calling this thing the domain. Okay, what are we doing? We got a model. Using the constraints, we found restrictions on R, which we're going to call our domain, and we're trying to optimize this thing or minimize it on our domain. So we're looking for the critical points. Okay, this thing is defined everywhere on the domain. Where is it? 0. Okay, here we go. 4 pi r minus 1,000 over r squared equals 0. And then we just work that out. We got r cubed is equal to 250 over 5. Okay, and that gives you r, that's a cubed, is equal to the cube root of 250 over pi. Okay. What is that equal to? That's approximately, I'm sorry it's so low, that's approximately 4.3. Yes, that's in the domain, so we keep it. Okay? Okay. That's in the domain. We only care about critical points that are in the domain or in the interval we care about. Okay, we check closed interval. We check continuity, so we can use closed interval method. We found the critical points, okay? When I say points, there's only one, okay? There's nothing there. There's only that one point there. That's in our domain. So life's good. Just check the endpoints, check the critical point, and we can finish. Evaluate at endpoints and critical points. Okay, so here's an endpoint. It's exciting, I'm going to do this live. Squared. All right. I'll put numerical values. If you want exact values, let me know. That's approximately 389, or 389.9. Okay. Evaluate at the critical point, which is that thing.
We're subbing it back into the original.
Perfect, exactly, yes, into the surface area expression, that's right. Okay, that's about, let's plug that into. There's a reason for this chaos. Okay. 348.7. Okay, and finally at the other endpoint, 500 over 6 pi square root. And that's about 360.8. Okay. All right. Alright, so there we go, that's the closed interval method. What do? We want to minimize the surface area, we pick the smallest one. What's the smallest one? Hey, it happened at the critical point. That's our smallest one, okay? So, here's our guide. So, our optimal radius is, whatever that was, cube root of 250 over pi, which is approximately 4.3. And that's in centimeters. Okay? And the associated height is 500 over pi that squared. Man, oh man. Okay, just using the fact that we had h equals 500 over pi r squared, we plug that optimal radius into here, and we get into that expression, and we get this as the optimal height. And that should be this, 8.6, which is suspiciously twice as big. Okay, so for an optimal can, you get the diameter is the same as the height. Okay, if you want a picture. Okay, 5. Okay, at 3 we would have been there. At 5 point whatever we would have been there. Okay, and our optimizer was there, pretty close. Okay, so there we go, use the closed interval method. Next time I'll show you something without the closed interval method. Again, we'll do the same problem except slightly differently. And then we'll move on. If you have any questions, come let me know. Tutorial at 5:30. Thanks. Okay, this was our example. We were told, and this is continuing lecture 4.8. We were told to design a can that had a certain volume, and we were given certain constraints on its dimensions, and we have to minimize the amount of material used, i.e. the surface area of the can. Okay, so we did that. We made a model, we wrote the constraint down in terms of the one variable we had, which is the radius. We found the critical point. And because our interval was closed, and because the function was continuous there, we used the closed interval method, evaluated at the critical point and endpoints, picked the smallest one, and that was our answer. Okay, I showed this in the tutorial, I'll show it again here. This is your updated graph. It's just zoomed in and domain corrected. Okay, so those are your endpoints, and that was the critical point, and you evaluated each of those, and you picked the smallest number, which happened to be here, the critical point. If the constraints have been such that, we've been told the radius had to be between, let's say, 3 and 4, okay? Then this thing would have gone from here to here, okay? There would have been no critical point in that interval, and when we evaluated the endpoints and the non-existent critical point, then we would have gotten that as our minimum, okay? So don't always assume that the critical point is going to give you your extremum, it could be at the endpoints, okay? It just so happened in this case the endpoints were on either side of the critical point, and we're looking for a minimum, and so on and so on. So again, for the record, check the endpoints and the critical point in the closed interval method. Okay, that's all good? Okay, we'll now do a slightly different version. So same example, but cut out that middle part. So there's no R must be this, and okay, so we're not going to say this time R must be between this and this closed interval. Okay, so it's going to be different now. There's going to be no closed interval. So example can again. But this time, no explicit constraints on the dimensions. Okay, so last time we were told something like the diameter has to be at least 6 centimeters, the height has to be at least 6 centimeters. I think that's what it said. No such thing this time. Now we have to figure out what to do, okay? And in tutorial, we began to talk about what we would do in this kind of situation. And we did an example. Okie dokie. Good? Okay, so exact same deal. We've still got our can. Okay, circular top. There's your radius, there's your height. Same constraint on the volume. The volume has to be 500 milliliters. From that, you can eliminate the height in your expression for the surface area. And we wind up again with this expression for the surface area in terms of the radius. Okay, exactly the same as before. And again, because of the volume constraints, we have height is equal to 500 over pi r squared. Okay. So, do exactly the same stuff as before, except now we don't have these constraints, so we have to figure out what our domain is. Okay, and the domain isn't now just between r between 3 and whatever, it's something else. So what's the domain here, folks? What can r not be?
0.
Can't be 0 and it can't be negative. Yeah? And that's it. Okay. So this time, we're not told the radius has to be at least this, the height has to be at least, and all this kind of stuff. We just have to figure out what makes sense physically, what makes sense given the equations and all this. And there's your answer. Okay? R has to be greater than 0. Okay, now, you could say you just look at the equation, sure, but keep everything in mind. Keep all the constraints in mind, keep physical sense in mind, all that sort of thing. So, what do you know? Okay, radius is a distance, okay, it's got to be non-negative. In order for this thing to enclose a non-zero volume, the radius has to be positive, okay? That makes sense. Or you could think that the radius has to be non-negative and the height has to be non-negative, and you combine r greater than or equal to 0 with this guy greater than or equal to 0, you can see that that's the same as saying r greater than 0. And all of that jives with this, okay? You know that r's got to be non-negative, and you know that you can't divide by 0, and that gives you this. So consider all the constraints, convince yourself that r's got to be greater than 0. Okay, good? Alright, so our domain is not closed this time. Last time it was closed, now it's not. Okay? This is open at both ends. So, and notice how realistic this is. Our radius can be arbitrarily large. Okay? So, if we're putting this in a store, we might give them very, very large cans. Okay, so our job is, our job is to minimize this thing, okay, for r greater than 0. Okay. Again, look at the equation, look at physical constraints, see what makes sense, and you've got your domain, along with anything they might tell you. Okay. It's always good to check if your function is continuous on the domain. So is S continuous? Yes. Okay. On that domain, which is an interval, so good, okay? So we've got our domain as an interval, and our function is continuous on it. The only place where this guy risks being not continuous is at 0, and that's not in that interval, so nothing to worry about, okay? So our function is continuous in our domain, which is an interval. So that's good news, and always good to check. Okay, again, our domain is, you could write this as, domain is this. Okay, the positive reals, and that's open, so we can't use the closed interval method, right? For closed interval method, we need continuity and a closed domain. We don't have that, so we can't use the closed interval method. So what do we do? Not closed. So no closed interval method. Okay. It is still true, okay, that if there are global extrema, they will be at critical points or endpoints. Okay? In this case, the endpoints aren't included. Okay? So there are no included endpoints. Does that make sense? Okay, so just as before, if there are going to be any global extrema, they'll be at either the critical points or the endpoints. In this case, there are no included endpoints because this thing's open both sides. So let's look for critical points. Okay, the derivative didn't change, it was the same as it was last time. Okay, so the derivative was 4 pi r minus 1,000 over r squared. Okay, and we did this already. It's exactly the same result as before. To look for the critical points, see where this thing is undefined, where this guy undefined. Let's say nowhere in the domain. Okay, so where's the function not differentiable? Where's the derivative not defined? Nowhere in the domain. Our domain's an interval, so nothing weird's going to happen. Okay, the only place where you risked having trouble was at 0, and again, 0 is not included. Okay, where's the derivative? 0. And we already solved for that, right? 0 equals 4 pi r minus 1,000 over r squared. And we wound up with r equals cube roots, possibly 250 over pi. Okay, good. And that is in the domain. Okay, if it wasn't in the domain, you just throw it away. Okay. Okay, good. So one critical point, and that's it. And no included endpoints to think about. Now again, we can't use the closed interval method, so we got to reason this out some other way. Okay, so to see that S has a global minimum there, okay, that's what we want to convince ourselves of. Again, first note, and this makes things easy and you don't have to think too much. Note S is continuous on the domain, which is an interval. Okay, so nothing bonkers is going to happen. And then there's 3 possible arguments from there. And see what makes sense to you. Then 3 possible arguments. Okay, first, this is sort of a variant of the closed interval method. Okay, so this is sort of a variant of the closed interval method. Okay, so for the closed interval method, we checked what's going on at the endpoints. And we evaluated endpoints and critical point, and then we made a conclusion. Here the endpoints aren't included, but let's see what goes on as we approach the endpoints. Okay, the endpoints aren't included, so let's see what happens as we approach them. So, as R approaches the left endpoint, and of course I've erased the expression for S. Okay. As we approach 0 from the right, what's going on? This guy shrinks down to 0, and this guy blows up. Okay? So the whole thing blows up. Good? Okay? This is my least favorite, by the way, of the three things I'm going to do. Okay? How about as we go that way? Okay, as we go that way, this guy shrinks to nothing, and this guy blows up, so the whole thing blows up. Therefore, our lone critical point, or critical number, gives the global minimum. Okay, what are we saying? If as we go that way, we go like that, and as we go that way, we go like that, okay, then the only critical point is going to give us a minimum. That should make sense, right? If you want to look at what the picture looks like, that's what that looks like, okay? We grow without bound going that way, we grow without bound as we approach our left endpoint 0, and so the only critical point there has to be a minimum, okay? So sketch that out, that should make some sense. Okay, so that's one way to think about it. Speak up if you have questions. Okay. Okay, second way to think about this is a global version of the first derivative test, which is what we talked about in tutorial. Global version of the first derivative test. Okay. And elegantly, I keep erasing the stuff I need. All right, that was our derivative. What do we do in the first derivative test? We look around a place where we think there might be a local min or max, and then we see if the derivative is positive or negative on either side, and then we come to a conclusion. Here, we're going to look everywhere, okay? Which is sort of what we've been doing anyway. Okay, if you want, you can rewrite this as follows.
Motion.
4 pi r. Man, this is falling apart. Okay, what's this? 4 pi r cubed minus 1,000. Cubed minus 250 over pi.
Motion.
Okay, so bring this guy up top and then factor out the 4 pi if you feel like it. Get that. Good? Okay. And then you look at the signs of the derivative, right? So you can draw one of these things, or there's a critical point, cube root of 250 over pi. What is the derivative doing? What is the function doing as a consequence? Nice. I'll find it again. Okay, so you've got an expression. You can either use that and plug in test values in here, and then see what the sign of this thing is. Okay, you can do that. Or you can fiddle around, come up with something that looks like that, and then see what the sign should be. Okay? So on our domain, r squared is always going to be positive. This guy's positive. This guy below here, okay, over here, is going to be negative. So, ta-da. And as we pass that, this guy is going to become positive. And so the whole thing becomes positive. Ta-da. Okay? Okay, negative derivative means the function is decreasing. Positive derivative means the function is increasing. Again, either you don't even have to do this. Either use this and test values to get the signs, or do something like that, or some other kind of reasoning to figure out what the signs are. Okay. Now, I'll write this out semi-formally. Since the derivative is negative for all r between 0 and the critical point, whoa. Okay, and it's positive for all r greater than the critical point, the critical point, therefore, the critical point gives our global min. Okay, so what are we saying? We're decreasing, the function is decreasing all the way from the beginning of the domain to the critical point, and then it's increasing forever after. Okay, so if you're getting something like that, then you're just going to have a trough there, and it's going to be the only one, and that's going to be the global min. Okay, so again, by contrast to the local sort of first derivative test, the normal first derivative test, where you really only care about what's going on nearby, here if you look at everything and you see that's going on, then you can say that that's a global minimum. Okay? And we've been drawing sort of stuff like that anyway, so this shouldn't be too bad. Does that make sense? Okay, we go like that, then we go like that, everywhere, and so there's a global min at that switch point. Finally, argument 3. Global version of the second derivative test. Okay, this means we have to find the second derivative. Okay, differentiate that puppy, and what do we get? We get 4 pi. Okay, plus 2,000 over r cubed. Okay, good? All right. Look at this thing. Again, global. You gotta look at it everywhere. Normally in the second derivative test, what do? You just look at the derivative and the second derivative at the critical point. Here you gotta look at it everywhere. Okay? Everywhere in our domain, so for all positive r, this guy's gonna be positive, so this guy's gonna be positive, and that guy's positive. So positive plus positive, positive, this guy's positive everywhere. Okay? That tells you you're concave up everywhere. Okay, what do you got? Since the first derivative at the critical point first derivative at the critical point was 0, and the second derivative is positive for all r in our domain interval. Therefore, we have a global min at the critical point. Okay, make sense? So what is that saying? Concave up, says we look like that. At the critical point, we've got a horizontal tangent, thanks to that. That guy tells us we're concave up everywhere, okay? And so obviously that's going to be a global minimum, okay? Again, concave up everywhere, and you've got the horizontal tangent there that tells you you've got a global minimum. Okay, so that's a global version of the second derivative test, which normally only looks at the critical point. Okay? Yeah.
Oh, what in terms of like for step 2, what is the stuff like factoring out
Say that one more time?
like the for step number 2,
Yeah.
like after the second step?
Yep.
Yeah, what was that?
What was it for?
Yeah.
It was for me to more easily see what the signs would be here and here. Okay, so I wanted to see what the sign of the derivative would be in this bit and in this bit, and it's easier for me to see that here.
But can you determine the sign from the first original?
Possibly, maybe. I can't as smoothly, so I figured I'd go to the second one, if you can as well. Okay. Again, you could from this, if you just plugged in like a value in here and a value in here and then saw the sign, that's cool, you can do, yeah. Okay, this makes sense? Okay, again, first one was look at what's going on, and then the lone critical point, if there's just one critical point, had to be the global minimum. Second version was, you're decreasing, then you're increasing if you look everywhere, okay? So you've got a global minimum at that critical point, and everything's continuous, so no trouble. And the third version was to look at concavity everywhere, look for the horizontal tangent at the critical point, and conclude there's only one critical point, you're concave up everywhere, at the critical point you're horizontal, and so you've got a global min, okay? So these are all sort of variants of the things we've already done. You guys got any questions about those? Right, okay. So there we go. Our minimum is there, okay? There's our global minimum, and that is that value. And so you can say the optimal radius is that, okay? And the optimal diameter, the optimal height you get by plugging that into the expression for the height, just as we did last time. Okay? And you get the same answer. Any questions about this? Okay. Fun fact, you can do these kinds of optimization questions with implicit differentiation too. But we're not going to do that. No questions? Okay. I did this in tutorial. Have a look if you want, once I post it. The slides are posted, the video is not yet. These slides. So there was the graph we got for the crop yield. I added 2 examples on the end. Again, I mentioned these in tutorial. I added 2 examples onto the end of this to show examples, biologically relevant examples of optimization. These are pulled from the textbook. Take them with a pinch or larger of salt or grain. This is talking about how honeybees appear to build their hives or their combs in such a way as to optimize the surface area of each cell. Okay, so what you're doing here is that's the expression for the surface area, and you're trying to minimize the surface area by appropriately picking that apex angle there. Okay, so you can give that a shot if you want. If you want me to do it for you, let me know. And there you go, there's the answer there. That's in the slides under lectures. Here's another biologically relevant example. This is talking about coughing, and this is talking about how during a cough it seems that the windpipe or trachea contract enough to maximize the speed of airflow. Okay? So again, what do? You've got a model for the speed of airflow, and you are trying to minimize that by picking the radius of the trachea appropriately. Okay? That one's quite simple. Again, give that a shot. If you got any questions, let me know. Another disconnect. Luckily, the thing's over. Okay. That's it for optimization. You got any questions? Let me know now or later. Okay. We're good? Okay. Ladies and gentlemen, our final unit. Let me just make a point. Some of these methods are easier in some situations than others, okay? In tutorial, I just did that thing because it was the simplest to talk about, I felt. Look at whatever works best for you in a given situation.